everyone, thank you so much for joining this video. We're going to be looking at Gibbs free energy change and entropy change today. So here are our learning objectives. We're going to be learning about delta H, which is not sufficient to explain feasible change, and the concept of increasing disorder. We're then going to learn about the equation delta G equals delta H minus T delta S, and what all the letters stand for. And then for a reaction to be feasible, the value of delta G must be 0 or negative. So by the end, we should be able to calculate entropy changes from absolute entropy values, use the relationship to determine how a delta G varies with temperature, and to use the relationship to determine the temperature at which a reaction becomes feasible. So now we're going to introduce the idea of entropy. And the basic idea is that entropy is equal to how much disorder there is in a system, in a substance. So the more disordered something is, the greater the entropy it has, and therefore gases have the highest entropy because it's got a million particles moving rapidly and randomly in many different directions. Whereas in solids, the particles are all fixed in all the particles are in a fixed position, vibrating, and so they have the least entropy. And by the second law of thermodynamics, this states that the entropy will naturally increase over time. And also, entropy is denoted by the letter S, and it's measured in joules per mole per Kelvin. So how does entropy change with temperature? Well, the third law of thermodynamics states that the entropy of a substance is 0, or very close to 0, at absolute 0. Absolute 0 is the temperature at which the particles have 0 energy, and this is why the third law states that the entropy, so the disorder of a substance, will be 0 when the particles have 0 energy, so they're not moving about at all. And this value of absolute 0 is actually at 0 Kelvin. So that will be equal to minus 273 degrees Celsius. And this third law also states that the entropy will increase with temperature. And this is because the higher the temperature, the faster the particles move. So, for example, when you're heating up a solid, the particles move about their fixed positions faster and faster until the intermolecular forces start to break, and then a liquid's formed. And so the greater the entropy, because the particles are moving about more, so there's more disorder. And so looking at this graph of melting a solid, so first the solid starts off with theoretical 0 entropy, and then as it's being heated, here, as it's being heated, the entropy increases because the particles are moving more about their fixed positions. And then there's a big jump between solid and liquid, and that's because there's a big jump in entropy, because in a liquid there are less forces between the particles compared to in a solid, whereas in a solid they're all quite fixed. And then when you heat up the liquid, the entropy starts to rise again. And then there's an even bigger jump between a liquid, the entropy of a liquid, and the entropy of a gas. And that's because in a gas, there are no forces between all the gas particles. And so there's a lot of entropy because they're all moving about randomly and in different directions. And then again, when you heat up this gas, the entropy will increase even further. Now we're going to see how to calculate entropy changes. And we use this formula. So delta S stands for change in entropy, and it's equal to the sum of the entropy of the products minus the sum of the entropy of the reactants. And so from this, we can see that in reactions when there is an increase in entropy, the delta S is positive because the reactants will have less entropy than the products. And in reactions where there is a decrease in entropy, then the enthalpy change will be negative, so it will be the opposite. And in keeping with the second law of thermodynamics, reactions in which there is an increase in entropy, those ones are favourable because the second law states that the entropy increases over time. And so we're going to look at this example, calculate the entropy change for this reaction. And so what we do is we use this formula. So we have delta S, and first we need the sum of the entropy of the products. And so these are these ones here. And the thing to remember with these entropy changes questions is that you have to multiply by how many moles there are of everything. And so first we have to have 2 moles times by the entropy of the carbon dioxide. And so we have 2 times 214. And then we have to add that with 3 moles of the water. So that's 3 times 70. And then we minus the sum of the reactants, so the stuff on the other side. So we have 1 mole of C2H5OH, which is minus 161. And then you can use a bracket, so you're minusing all of the sum of the entropy of the reactants. And then you add on 3 of this 205. And then you just plug in all the numbers, and this comes out to be minus 138 joules per mole per Kelvin. And you need to remember the units of this entropy. However, they have given it in this question for us. And so from this, we can say that this reaction is not favourable as there's a decrease in entropy. And the way in which we can make it more favourable is by adding heat. So by raising the temperature, that will increase the entropy. Because by increasing the temperature, we'll increase the number of particles with the activation energy. And so more products will be formed. So that means that this sum of entropy of the products will be much bigger. And so this delta S should hopefully be positive. Sometimes we might be asked to predict whether entropy changes will be positive or negative without them giving us all the values to calculate the actual entropy change. And so, for example, predict whether this reaction will have a positive or negative entropy change. And we just have to look at the equation. So we've got gas on one side and solids on the other side. So if we remember the equation, delta S equals the sum of the entropies of the products minus the sum of the entropy of the reactants. If we remember this equation, it should help us, because if we kind of imagine everything that goes into these values, then we should kind of get a gauge as to whether as to what the value of the delta S will be. So for the sum of the entropy of the products, that means these gas molecules here, we've got 3 molecules of gas. And for the sum of the reactants, we have 1 mole of solid. And so what we know about entropy is that gases have the most entropy, because they have the most disorder, because all the particles are moving randomly and in all different directions, compared to solids, where their entropy will be very, very small because all the particles are in fixed positions. And so this sum of the entropy of products will be really, really big, and the sum of the entropy of the reactants will be very small. And so we know, we can predict that this change in entropy will be positive. And that's because 1 mole of solid will form 3 moles of gas. And so that means that there is an increase in the entropy of this reaction. Now I'm going to introduce Gibbs free energy change. So Gibbs free energy combines enthalpy change and entropy change. So this is an equation we have for Gibbs free energy. So delta G is the change in Gibbs free energy. The delta H is enthalpy change, as we've already learnt. And then the T stands for temperature. And then the delta S is the entropy change. Now we know that a decrease in enthalpy, so a negative delta H, so an exothermic reaction, is more favourable in a reaction, and an increase in entropy change, so a positive delta S, is more favourable in a reaction. So overall, if delta G is less than or equal to 0, then the reaction is feasible. And feasible just means that the reaction can take place. Sometimes the word spontaneous is used, which means thermodynamically possible, which is quite similar to feasible, but it is better to use the word feasible. And we can see this because if we have a look further at the equation, delta G equals delta H minus T delta S, it's favourable for delta H to be negative. So if this is negative, and then we're minusing the delta S, which is favourable when it's positive, that means that the delta G is feasible when the reaction is less than or equal to 0. So when delta G is less than or equal to 0, then the reaction is feasible. And that's because the enthalpy change is favourable and the entropy change is also favourable, because if we have two negative figures, then that will ultimately be negative. And it's very important to also note that temperature is included in this formula. And so that means that the feasibility of reactions actually depends on the temperature as well. So we can make things feasible when they're not feasible by altering the temperature. However, one thing to note is that even though a reaction may be feasible, the activation may be too high, the activation energy, may be too high for the reaction to actually take place. So here is a nice table to summarize how Gibbs free energy changes with temperature. So if we have a look at the first example, if we have a negative enthalpy change and a positive entropy change, then the delta G will always be negative, so it's feasible at all temperatures. And so we can see this because if we've got delta G equals delta H minus T delta S, if we have this as a negative, and then we have minus, and then the delta S is positive, that means that this will always give a negative value, no matter what the temperature is, because the temperature can never go below 0. It'll always be positive. And then for the second example, we have a negative delta H and a negative delta S. So we've got T and then a negative delta S. And this means that if we lower the temperature, then the delta G will be negative. But if we have a higher temperature, then the delta G will be positive. And we can see that because what we have right now is that we have a negative plus T positive. And so if this T positive is equal to this minus delta H, then what we have is that this delta G is equal to 0. And this is the tipping point, whether the reaction is feasible or not feasible. So which means that when we have a very, very high temperature, that means that this will exceed the negative, so the negative delta H. And what will happen is that we'll have a negative plus a very, very big positive. So then delta G will be bigger than 0, making the reaction unfeasible. Whereas if the temperature is very, very low, then we'll have a negative plus a very small positive. So it still won't, the delta G still won't exceed 0. So then we have delta G is smaller than 0, making the reaction feasible. And we can go along and apply this same kind of logic to the other two examples we have. So we have for a positive delta H and a positive delta S. So if we lower the temperature, then the delta G will be positive, and if we raise the temperature, then the delta G will be negative. And for the last one, we have a positive delta H and a negative delta S, and the delta G will always be positive. And I'm going to explain this by saying if we have So writing out the equation again, we have delta G equals delta H minus T delta S. So if this is positive and if this is negative, because the temperature can only be positive, it can't go below 0 Kelvin, that means that this will always be positive because we've got two minuses here which equal a plus. So we'll always have that delta G is bigger than 0, so it will never be feasible at any temperature we use. So now we're going to discuss entropy at changes of state. So we're going to look at the example of melting something. So below the melting point of a substance, Gibbs free energy change is positive, so melting is not feasible. So we write delta G is bigger than 0. At the melting point, Gibbs free energy change is equal to 0. So we have delta G is equal to 0. And this is the tipping point as to whether it's feasible or not feasible. And then above the melting point, Gibbs free energy change is negative. So melting is feasible. So from the point where Gibbs free energy change is 0, the reaction becomes feasible because we know that if delta G is less than or equal to 0, then the reaction is feasible. So for this example, the enthalpy change for melting potassium chloride is 25.5 kilojoules per mole and the entropy change is 24.5 joules per mole per Kelvin. Calculate the temperature at which potassium chloride melts. Well, we would write out the equation, so we have delta G equals delta H minus T delta S. And then we would set delta G to be 0 because this is the point where the reaction becomes feasible. So we set that as 0. And then we put in the enthalpy change, which is 25.5. And then we have minus T, and then we have the entropy change. Now, one thing to note is that the entropy change is given to us as joules per mole per Kelvin. However, it needs to be in kilojoules per mole per Kelvin because the enthalpy is measured in kilojoules. And so we need to convert this to kilojoules. So we would have to divide it by 1,000 or times 10 to the minus 3. And so rearranging this gives us minus 25.5 equals minus 24.5 times 10 to the minus 3t. And so we find T to be equal to 1040.8 Kelvin. Now we're going to look at some graphs of Gibbs free energy change over temperature. So on the left, we have the equation of delta G equals delta H minus T delta S. Now we know we can plot straight line graphs by using the equation y equals mx plus c. This is the equation for a straight line, so the general equation. And so if we fit our delta G equation into a y equals mx plus c format, then we can plot straight line graphs. And so what we do is we make the delta G y, and then we have mx here, and then we have a plus c. So we have that y is the delta G, x is our t, m is our minus delta s, and c is our delta h. So if we plot a graph of delta G over t, then we get a graph of y over x. And y stands for the y value, x is the x value, m is the gradient of the graph, of the line graph, and c is the y-intercept. So where this line crosses the y value. And so from this, we can see that if we plot a straight line graph, then we can find the enthalpy change by seeing where it crosses the y-axis, and we can find the entropy change, the delta S, by doing m equals delta y over the delta x, and this would be negative. So if we worked out the gradient of the line and negated it, then that would give us the entropy change value. And so if we look at the graphs on the right, on the first graph, we have an endothermic graph. And this is where the delta H is positive and the delta S is also positive, because we see that the gradient of the line is negative, but that equals the negative of the delta S. So the delta S must be positive. And so we see that on the graph, from this point to this point, the reaction is not feasible. And this is because delta G is bigger than 0. So the reaction is not feasible. However, at this point, the reaction becomes feasible because this is where delta G is equal to 0. And then we have that this bit of the line graph is where delta G is bigger than, is smaller than or equal to 0. So then the reaction becomes feasible. So we can actually read off the temperatures where this reaction will be feasible using these kinds of graphs. And then at the, looking at the bottom graph, this is an exothermic graph, and we can see that because we have a negative delta H, because where it will intercept the y-axis will be somewhere down here, so it'll be negative. And then the delta S, the entropy change, will be negative because the gradient of it is positive, but the gradient is the negative of the delta S. And so again, we can see where it will be feasible and where it will not be feasible. So from this point to this point, this is where delta G is smaller than or equal to 0, so the reaction will be feasible. And then from this point to this point, we have that delta G is bigger than 0, and so the reaction is not feasible. If we do have a graph that looks kind of like this, so we've got the temperature on the x-axis and delta G here. If it looks something like this, and it looks as though it will never cross this x-axis where this delta G is equal to 0, then that means that this reaction will never be feasible. So this is never feasible. And this is because delta G is always bigger than 0. Now we're going to look at some questions. So for number 1, predict whether there will be a change in entropy for the following reactions. For A, sodium chloride solid to sodium chloride aqueous. And we know that entropy increases when you go from solid to gas. And that's because the particles move about more, so there's more disorder. And so if we're going from 1 mole of a solid to 2 moles of aqueous ions, 2 moles because we've got 1 mole of Na plus aqueous ions and 1 mole of Cl minus aqueous ions, that means that the entropy will be increasing because we've turned them into liquids, and also the disorder has increased. And so delta G, and so delta S, so the change in entropy, will increase. And then for B, we have 4 moles of gas on the left, and this goes to form 2 moles of gas on the right. And this is quite easy to work out because they're both gases. So if we're going from more moles of gas to less moles of gas, then that means that the entropy is decreasing because we've got less gas, so we've got less disorder. And so delta S decrease. And then for C, we've got 2 moles of gas on the left and also 2 moles of gas on the right. And that means that there'll be very, very little change in entropy because we've got the same number of moles of gas on each side. And so delta S remains nearly the same. And then finally for D, we've got we've got a Ba plus and 2 NO3 minuses. So we've got 3 moles of aqueous ions for the Ba NO3 and then for the K2SO4 we've got 2 K pluses and 1 SO4 minus, and that's another 3. So we've got 6 moles of aqueous ions on the left. And on the other side, we've got 1 solid, and then we've got a K plus aqueous ion and an NO3 aqueous ion, but we've got 2 of these, so that means we've got 4. And so we form 4 moles of aqueous ions and 1 solid. So that means that the entropy will decrease because we're forming a solid, and the entropy of the solid is much less than for aqueous ions. And so delta S will decrease. So what we do first is we write out the equation. So we have delta G equals delta H minus T delta S. And so delta G we're trying to find, so that equals delta H, which is minus 185, then minus T, which we always need in Kelvin, so they've nicely given it to us in Kelvin. So we use minus 298, and then that will be multiplied by the entropy change. Now the entropy change, you have to realise, is measured in joules per Kelvin per mole, and delta H is measured in kilojoules per mole. So we need to convert the delta S always. So we convert this delta S to kilojoules per mole per Kelvin. And you can either do that or convert the delta H, it's up to you, but they both have to have the same units. And so then we have to multiply by times 10 to the minus 3 or divide by 1,000. And then that gives us a delta G value of minus 191 kilojoules per mole. And then for B, is this reaction feasible at this temperature? We know that when delta G is smaller than or equal to 0, then that means that the reaction is feasible. And so this means that this reaction is feasible at room temperature. So room temperature is 298 Kelvin, and we've worked out the delta G for this temperature, and it's minus 191, and that's smaller than or equal to 0. So then that means that the reaction is feasible. And then for C, explain why this reaction may not occur at room temperature. The main reason is that the activation energy required for this reaction could be very, very high, and so this is why it could maybe not occur, even though the reaction is very feasible. So the activation energy of the reaction is very high. Hi everyone, thank you so much for joining me for this video. We're now going to look at some harder questions for entropy and Gibbs free energy. So for the reaction, calculate the enthalpy change and entropy change given all of these values. So because we're only given the enthalpy changes of formation, that means we need to set up a Hess's law kind of cycle. So for A, we have 2NaHCO3, which is a solid, and that goes to form Na2CO3 solid. plus carbon dioxide gas plus H2O, which is also gas. And this is the enthalpy change that we're trying to find. And so because we're given the enthalpy changes of formations, that means that we're using the constituent elements of these compounds to form them. So we have sodiums, and we also have hydrogens, we have carbons, and also oxygens in order to form this and also this. So now we need to balance these equations. So we need 2 of this sodium because we've got 2 here and also 2 here. And then we only need 2 hydrogens, so that's fine. And then we need 2 of the carbons. And then for oxygen, we need 3 plus 2 plus 1, which is 6. So we need 3 oxygens. And this will be the delta H of formation of this sodium hydrogen carbonate. So that'll have to be 2 times because we've formed 2 moles when the definition of the enthalpy change of formation is when we form 1 mole. And then for this side, we have the enthalpy change of formation of the sodium carbonate and the carbon dioxide and the water. So now we can start to put the values on. So we have 2 times minus 948, and that equals minus 1,896 kilojoules per mole. And then on this side we have minus 1,131 plus minus 394 plus minus 242, and that all adds up to be minus 1761 67 kilojoules per mole. So now we can apply Hess's law to find the missing delta H. So I'm going to say that this is going to be the start and this is going to be the finish. And so what we get is minus 1896 plus the delta H is equal to minus 1,767. And rearranging that gives us delta H equals plus 129 kilojoules per mole. And then we're going to find the entropy change. So that's delta S. And we know that delta S is equal to the sum of the entropies of the products minus the sum of the entropies of the reactants. And so we use this formula. So we have that is equal to the products. So we have 1 of the Na2CO3, so we need 136. We have 1 carbon dioxide, so that's 214. And then we have 1 water, which is 189. And then we minus, and we've got 2 moles of this sodium hydrogen carbonate. So we need 2 times 102. And this gives us plus 335 joules per mole per Kelvin. So for B, it tells us to calculate Gibbs free energy change at 298 Kelvin. So we have the equation delta G equals delta H minus T delta S. So now we can just sub in all of the numbers because we have all of them. So that's equal to 129 minus 298. And remembering to convert the delta S again, it'll be 335 times 10 to the minus 3. And this gives us plus 29.2 kilojoules per mole. And then for C, it asks us calculate the temperature range over which this reaction is feasible. So remembering when a reaction is feasible, that's when delta G is less than or equal to 0. That means that if we set delta G to be equal to 0, then we can see when the tipping point is. So when the point it begins to be feasible. So if we set it to 0, and then we've got 0 equals delta H minus T delta S. So we sub in delta H and delta S again. So it would be 129. But then the T is now unknown. And then we have 335 times 10 to the minus 3. Rearranging this gives us 335 times 10 to the minus 3t equals 129. And then to get t, you'd rearrange it again, and we get t is equal to 385 Kelvin. And so the range in which this reaction is feasible will be when T is actually bigger than or equal to 385 Kelvin. And we see this because if we write out the equation again, we have delta G equals delta H minus T delta S. And we've got that delta H is positive and delta S is also positive. And then we've got the T. So at 385 Kelvin, delta G is equal to 0. If we increase T, then we would have a positive minus a very big positive. So then that would mean that delta G would be less than 0. However, if we decrease the temperature, so if we decrease the temperature, then it would be positive minus a very small positive number. So the overall delta G will still be bigger than 0. So that means that the temperature has to be bigger than or equal to 385 Kelvin for the reaction to be feasible. And then for D, explain the sign and magnitude of the entropy change. So the entropy we worked out as positive, and we can predict this from the reaction equation, because we start off with 2 moles of a solid, and we end up with 1 mole of a solid and 2 moles of gas. And so what that means is that because 2 moles of gas are formed, that means that the entropy has increased because the disorder has increased, because gases have a higher entropy. And so that's why the sign of the entropy change is positive. And also the magnitude is quite big at plus 335 joules per Kelvin per mole. And that's because 2 moles of gas are formed from solids. So to get from the solid to the gas, the entropy has increased by a significant amount. And then for E, explain the sign of the enthalpy change. The enthalpy change is positive. This reaction is endothermic, and that's why the enthalpy change is positive.